All right, welcome back. We are Game 3001. That's Artificial Intelligence in the winter 2021 semester at George Brown. And it's week 11, but it's kind of like teaching week 10 because we did our midterm and la la la. So again, we're teaching week 10 and we're going to get into state machines today, which I would say is definitely a mainstay for doing AI, and we'll talk about what that means in a bit. So where are we? We're sitting at week 8. So this week again, lab 8 will be due Sunday, just like normal. Labs are going to be due Sunday. I want to also remind you that assignment 3, I know some people haven't started it. That is due this Sunday at midnight. So guys, it's been a few weeks now since I've released assignment 3. Again, sign up for a group of up to 3 members, and you need to use A3 groups, not A2 groups or A1 groups. It won't work. If you haven't had a chance to do that, please do that ASAP. Sign up for groups or else it won't work properly. And then assignment 4 is based on assignment 3. So if your assignment 3 is terrible or if it doesn't work, A4 will be a disaster for you. So please make sure you focus on the requirements. You can see how long it takes. It's not going to happen that you can do it overnight, right? Yes, so Sean's asking if on the assignment 3 outline it says we have to overlay on top of nodes, and the nodes aren't display objects. No, they're not. You don't show nodes; they're invisible, right? What you'd want to make, Sean, is you'd want to use nodes as navigation objects, right? Remember what we talked about when it comes to assignment 3, and since you're asking, let's just get into that. We had a little diagram that I was using for you guys for assignment 3. Remember this little diagram, right? I'll bring it up here like this. And I'll just drag and drop this in. This one here, right? So even though I'm showing these little nodes here, these are just as an example of locations on our map, right, where our enemies can travel to from a navigation perspective. And again, you can make yours, of course, more organized than this. This is just an example of how it might look if you had several enemies, your base enemies, running around the screen, right? You're going to have obstacles. And then what you're going to do is invisibly, so in the background, you're going to have a location, or a transform position for each of the nodes, the navigation nodes, on your screen. So for example, your base enemy can only go to the next node, the next node, the next node, the next node. I recommend this. And then what we want to check is, do each of the nodes have line of sight, as an example, with the player object? And remember, because one of the things that you're going to do is if it has line of sight, you want to make sure line of sight is working for assignment 3, as well as a detection radius. And then your beautiful little map that I asked you to make is just going to be overlaid on top of the invisible nodes that are here. Obstacles, obviously, if you're going to make anything obstacles, like for example, if you're going to make it so that the map has a border on it or something like that, then you're going to have to make it so that the player can't leave the map. As well, when the player comes to the obstacles, you're going to have to use some kind of collision detection scheme. That's all it is. Yeah, no, not decision tree nodes. It's just nodes, as in like for you to travel. Path node, more like path nodes is what they are. Okay. Back to this. So that's assignment 3. Let's do this Sunday again. And again, like I said, assignment 4 is based on assignment 3. So guys, please do not forget, this is an important one because these 2 assignments are heavily weighted, for this semester. So if you don't get assignment 3 done, assignment 4 will be a disaster and it'll affect your mark. Please don't do that. Work on assignment 3 together. It takes some time to do things properly. There's some artwork involved that you have to grab, animations we're asking for, lots of stuff that's involved with assignment 3 and 4. You're making a little game for the most part with assignment 3 and 4. So work diligently with your assignment partners to make sure that you get things done. Okay, and don't, if you haven't started yet, I really would hook onto this as quickly as you could, right? Like today would be a good day to get going on it. All right, so that's just my recommendation again, but it's totally up to you. All right. Any questions around assignment 3 or 4? It's upcoming. It's due this Sunday, and everything we're doing in our class again is based to help you to do assignment 3 and 4. That's why we're doing those things. All right, so no questions. I'm gonna move on now, and I'm looking on YouTube as well for any questions for people on YouTube. All right, so where are we? We're sitting at week 11. We've got a few short weeks left. So, you know, in 4 weeks, we're looking at our final test. Again, we'll give you more details as we approach that. We've talked about so far decision trees, which we've been focusing on making last week, behavior trees, and state machines. Those are the 3 things we talked about, you know, kind of when we discuss stuff. State machines is going to be something we're going to be more in detail today because you should have known how to make state machines. I know that Alex has probably covered kind of state machines 101 for you in your game fundamentals courses, but we're going to continue to talk about state machines from an AI perspective today. Next week is where it gets interesting. We start talking about goal-oriented behavior and utility AI, and how utility AI kind of connects to machine learning concepts with reinforcement learning, so we can make an intelligent agent, not just an agent that does pathfinding and that kind of stuff. Once we get into goal-oriented behavior, now there's every agent will have their kind of, you know, priority, if you will. Why are they there? You know, kind of stuff, and it'll create more realistic AI agents, right? When you get into this part. One thing to also note is I know that people have asked, as an example, about, you know, deployment, and are we going to deploy everything that's here? Am I going to show you everything that's here in lab? No, I can't. There's no way that I can show you every piece of code that we're talking about in lab. And the reason for that is because we have to focus on the labs being helper for your assignments, number 1. And second thing is the concepts that we're introducing here in this course are something that you can expand upon on your own, or in the workplace. You've heard about them. You know how they work. You may not have never deployed, for example, a you know, a utility or machine learning, reinforcement learning kind of structure. We've talked about it, and I think it's good for you to understand what's out there and other possibilities. There's a lot of things we can research in AI, and there's no way we can possibly cover everything in this course. There's just no way. This is really an introduction to AI, and I think this is a great start. Once you've got these concepts, then you can build upon them. That's the idea behind it all. All right, so hopefully that was helpful. I have another question from Cameron. There is no A2. There's no AI2. I wish there was. No, there is not. But we use AI later on, Sinan. Cameron asks, in this version, so you're talking about assignment 3, will the enemy be breaking away from the patrol path ever? Well, let's take a look. I'm glad that you asked that question. Again, I'm asking for questions around assignment 3 because assignment 3 is going to be due this week, and you're not going to see me again. So I might as well ask this, you know, questions now. Let's talk about it. So let's take a look at what it tells you. So play scene, which you've done before, and then you get into this, some debug keys and a debug view you have to work with. Sound effects and those kind of things are important. Player combat abilities, you'll be able to fight and so on. And then here comes your base enemy class. Your base enemy class, you know, as an example, it's going to have a health bar and so on. It's going to have animations and sound effects. It's going to use line of sight, and it's going to have a detection radius. And that's really what it does. So what happens is when the game starts, so that's in the play scene. Let's go back up to the play scene. And the way this works is your play scene is basically going to allow your enemy to wander around. So your enemy is going to basically just patrol. And I don't think that in this version, I'm just going to go through it, make sure that we included all the right stuff. But I think that your enemy AI is just going to patrol the entire way. I'm just looking through it, make sure that I've got it set up here. Yeah, here it is. Your game will include a base enemy class, and the base enemy object will move, patrol along a predetermined path of nodes around the map. The base enemy game object will have a health property, and what you're going to be able to do is you're going to be able to injure it. So you can test this version, assignment 3, is really you trying to hit the enemy and do close combat and ranged attacks with your player. So it's all around your player. Can I attack the enemy? Can I injure the enemy? Can I kill the enemy? You know, that kind of stuff. There's no talk of respawning or anything else like that here, but you may want to make it so that the enemy you can reset, maybe with some kind of debug keys or something like that. But that is what it's going to do. There should be some sound effects. So build in all the enemy animations and all those kind of things. And then also, I would be able to test. I would recommend you test, line of sight and detection radius. And I think I've asked for this with your debug keys, right? So if you look at the debug part up here, it says when the user approaches the H key, your program will toggle into debug view. Again, you can use the tilde key, the H key, something like that, which will display line of sight rays, okay, and detection radius. So line of sight rays are coming from the enemy or even from nodes, path nodes, and detection radius from the enemy, collider boundaries, and node points. So the actual node points will be showing up in the map as an overlay. All right, so that's what's happening here. And then the P key, the base enemy movement will be toggled between idle and patrol. So that's the only time that they're going to change. And what you may want to do, again, knowing that in assignment 4, the AI is going to have also some animations for attack, you may want to get all those animations and try and build them in as early as possible so that assignment 4 becomes easier. But again, you don't need it. All you need for this assignment is an idle and a patrol animation. That's all the things you need for your enemy. Okay, so that's something that you need. Okay, so hopefully you guys have that. Please read the document. Samantha says, is it okay if the enemy's health bars are listed in the top left corner of the screen, or do you have to have their heads move with them? I prefer their heads, and so that they move around and you can see it. Could you have it in the top left corner? I mean, I guess you could. I didn't specify that there would be, but they need to have a health bar associated with them. And it really depends on your design decisions. A lot of times, again, you could look at the top left corner, but remember, your eyes usually are focused on the screens. From a design perspective, I'm talking about game design, a lot of times you see enemies with the health bar above their heads. And the reason for this is that way, when you're fighting an enemy, you know what their status is, right? And you don't have to look, your eyes don't have to look away from the theater of battle. They don't have to look up in the top left corner or top bottom corner. And that's why a lot of times you have all your stats like kind of in the field of view. But it really depends on your style. If it's, if you make a game, you might want to make your game, you have your health bar somewhere else. It just may not be as effective. It really depends on how you lay them out. So it's up to you. I don't think that I'm going to limit you. I don't think Alex would limit you either. As long as you have a health bar, I don't think we said anywhere that the health bar has to ride along with your their enemy, and even for the player also must have a health bar, but it doesn't say that it has to ride along with them, right? I mean, we have to give you a little bit of leeway here. So yeah, if you wanted to make it so that the health bar is in the top left corner, you could, but again, design wise might be better if they're kind of over the heads of the enemy, or there's some other kind of indicator, hearts, symbols, a color, there's lots of other ways of doing it, the same thing, and showing the health of your enemy. Some people actually use a filter for the enemy, and I've seen that before in other semesters, where if the enemy gets hit, they become more and more red, right? Like there's actually a color filter, and then when they're all red, they're or as they approach more, you can see that they're dying or whatever. There's different ways of doing it, so it's up to you. All right, so that is assignment 3. We need to get up to the other stuff we're talking about today, which is state machines. If you have more questions about assignment 3, please hit me up during lab. Okay, so let's get into this. So again, when we think about this, we have some kind of another mode. So far, again, we've talked about the second half is all about making decisions. And one of the ways we can switch between making decisions is to switch states. Again, I'm in one state or another state, right? We're going to talk about that in a sec. And actually, we've introduced state to you when it comes to game state, okay? So we have, we can use decision trees, and we can also use some kind of random decisions with decision trees, right? But a lot of times, a very simple way of doing stuff is with something called state machines. And state machines, they're also called finite state machines, and usually is, and it says it's the majority of decision-making systems. I think for older games, yeah. A lot of newer games use decision trees, but for older games, definitely we use state machines, and the reason for that is because they're very simple. So a state machine, each AI, each autonomous agent occupies one state at a time. So basically what happens is I'm in patrol state, as an example. And then actions and behaviors are associated, even animations, sound effects, they're all associated with that one state, right? So as long as I'm in that state, I'm continuing to carry out the same action, whatever that action is. I'm in attack action, I'm using patrol action, I'm doing whatever. We've already established some actions, right? But state machines, what they do is they have a set of transitions and they have a set of conditions. Okay, we're going to talk about these, and they're a little different than regular state machines that we've seen as well. So each state is connected by transitions, and each transition leads from one state to another, right? Whatever the target state is going to be. So you're leaving a current state and you're going to a target state and you're transitioning, okay? And there's associated conditions with them as well. So if the conditions are met, then we want to start transitioning from one state to the other state. And when we're into the new state, then we're now we're doing that new action, whatever that new action is going to be. So whatever the conditions happen, they trigger a transition, and then it's followed into a new state. Okay, so these are the words we're going to use. So so there's four components that are part of a state machine. Some kind of behavior that may or may not produce actions. Okay, some kind of behavior. It could be, as an example, idle behavior that doesn't produce any actions, it's just idle, right? Transitions, which are movement from one state to another. And some kind of rules or conditions which are going to, when met, they're going to trigger, you're going to set up a series of events that are going to trigger the state change, whatever it's going to be, right? And a state machine must have some kind of initial state, right, which is a starting point. So, for example, the idle state, the patrol state, whatever it's going to be. And then some kind of current state, which understands what happened before. Where did I come from? What state did I move from? Where did I transition from? So the way that looks from a diagram perspective is something that looks like this, right? I have an initial state that starts off as on guard, all right? So that's the on guard state. And then I have a some kind of trigger that moves me from on guard to fight, all right? A trigger. And the trigger in this case is see small enemy. See small enemy, I fight. And then I'm in fight state. So if I'm losing the fight, notice that this is a directive graph. If I'm losing the fight, then I run away, right? Now this state machine is incomplete as well because there's no way back to being on guard, right? If I win the fight. I run away in my runaway state as an example. And if I'm good, I go back. If I escaped, I go back to be on guard. So one arrow that's missing that I would see is missing in the state machine as an example. Let's draw it. So we'll draw a line. See if we can draw a line here. And the line should go really from, okay, no, I can't draw a line. Silly. Line, width, font. draw a line. So yeah, so it should go from here to there, right? And this state, because if I don't have a way of getting out of here, as an example, right? There's no way out. The only way out that I can do is lose the fight. So this guard would be a very weak guard, right? Weak guard that only sees a small enemy to fight, otherwise they run. That's what they do, right? But if they might win the fight with the small enemies. So if what we should then say is when the fight is if the fight is won, so win fight. If I win my fight, then really I should be able to go back, right, to the previous state, right, which is the guard state. I should be able to do that. And I have limited controls here, guys. Sorry for my annotations. So you're gonna have, this is a zoom thing, not a thing. So if I win the fight, then I go back, right, to on guard, right, and that's how it should be. So this is kind of the way you would map it out. Now you might look at this and go, well, it's kind of similar to what trees did for us. They do, but there's something that's new, which is transitions, and transitions are directed arrows that go from one state to the other, right? So you may not have a transition, as an example, to go from back from run away to back to the fight. In this case, if they're losing the fight, they're never going to fight again. There's no way they can get back to this point. Once they're losing the fight, like for example, maybe losing the fight might mean their hit points, their health is low, right? And the enemy's health now becomes more powerful than theirs, right? Somehow. Then this triggers the losing the fight, and they're always going to go here, and they're never going to go back to fighting again. But they may go back to on guard, right? So now the big enemy, if the big enemy is there, they might go back and forth, right? Because now maybe seeing a big enemy, well, if they lost the fight and they ran away and they're going back on guard, if they see that enemy again, now they're going to run away again. And they're going to keep on doing that transition. One thing to note is the transition that happens, right, that goes from on guard to fight, right, is based on a trigger. So this trigger event, sorry, let's get out of annotations here for a second, and let's clear all my drawings. So this trigger event, which is right here, clear all my drawings, I said. This trigger event, which is right in here, right, this one right here, is seeing small enemy. How do I see anything? Well, it's not just line of sight, but also understanding. I see and detect that the enemy is bigger or smaller, which means somehow the guard will be able to know external information like health. I can see that this is a bigger guy, or health, he's stronger, or maybe there's, I don't know, the potential for doing more damage, or whatever that they're able to detect. Okay, they need to make a decision based on the condition. Okay. So states are on guard, fight, and run away in this case, 3 little states, and each state has a set of its own transitions. So we can use UML, which is Unified Modeling Language, to draw a chart if you like to. And one thing we want to always draw is states, transitions, and conditions. A solid circle in the figure is that has only one transition without a trigger, right? And that's the initial state, okay? So we have the same kind of thing. In a decision tree, the same set of decisions is always used, and any action can be reached at any time through the tree, right? Because you go back to the tree again, and you go back and do it. In a state machine, though, only transitions from the current state are considered, right? So it's almost like a graph, and the graph is, there's no other way to get out of, to do another state. There's no connection, let's say as an example, between one state and another state if there's no transition to that other state, right? So that's one thing to know. So again, we talked about state machines, but they're usually called finite state machines. And why? Because there's a finite set of actions that they can do. Okay, that's one kind of a very high way of looking at them, right? A finite state machine also is used in other places to parse text, and a lot of times is a simple switch case statement that allows us to parse a decision. We can still use a switch case, and I think this is not a bad structure for a state machine, but again, there's a higher order class that we need to use in order for us to accomplish the move from one state to another. So, so again, there's a bunch of different kinds of implementations that we can use. And one of the things they talk about in the book that we use as a reference for this course is that it's hard just to say that there's like a one kind of a silver bullet that is the way that all state machines work like. Sophia, sorry, I'm looking also. I got a couple people on YouTube here. And Sophia, I'll answer that question during lab, or when it comes to collider boundary. I'll come back to that. And Neil says he's talking about his game. So I'll get back to that, guys, in a bit. Sorry, I'm just trying to make sure that I'm keeping my mind on things. I don't have a timeline or of when you guys put those comments in. I'm trying to look at both. Actually, all three things. I'm looking at Discord. I'm looking at the comments here in Zoom as well as YouTube. So bear with me. All right. So yeah. So that's what a state machine is. A state machine is, there's no one algorithm that fits them all because every state machine can be done slightly differently. So so really the problem is we want a general system that supports arbitrary states, and our state machine will conform to the structure given above and only occupy one state at a time. That's important. So that means you can't have multiple states in play at the same time. So the way to do that is we're going to have some kind of generic state interface, and the state interface is going to have all the components that we need in order for us to make individual states. Again, remember that we're probably going to make a superclass, an abstract superclass state or state machine, and then from there we're going to make our own, kind of a class. We also need to have some kind of an update function, and the update function is called in the state machine every frame. That state machine's update function is going to be called, and think about what that is. Just like we had our update function in our decision tree to update. In this case, the update of the state is going to keep checking every frame to see if the state has changed. Has the state changed? Has the state changed? And then once something has been triggered, it's going to change the the active state to something new. Okay, and the trigger is based on a decision that's going to have to be made. Okay, so something that we've seen before in the past. I'm just going to skip through this to get to some of the code examples. So here's an example, and I'm talking code this time around because I think it's worthwhile to look at some of this before we go forward. So let's take a look. So here's our class state machine. I want you to think about this class state machine that we're going to be working with later on as an abstract superclass, something that we're going to set up and create a new state. Okay. But even if it's not abstract, let's think about this. And our initial state, we're going to set up some kind of state. We don't know what it is. Our current state is going to be equal to our initial state for now. So a lot of times we have our initial state as something like idle. And many times, by the way, we use states that are enumerated, right? Like, for example, the idle state is an enumerated state that we use, right? The attack state is an enumerated state, as an example, because I like to use enumerations or enums to go from one state to the other. All right, and then we have our function update, and the function update returns an action array. That's what it says here. This is what this arrow means when we look at the pseudocode. So our update function returns an action array, right? And the action array can include one or more actions that need to be followed, all right? And by the way, you can always mix and match state machines with decision trees and so on. There's nothing wrong with doing that. Sometimes you need to do that kind of thing in order for you to produce the effect that you want. All right, so triggered, that is whatever the transition is, and it starts off as null, so there's no transition triggered. For every transition in the states transitions, I may have a bunch of transitions here that I kind of build up my, because I'm going to have a transition array, right? For every transition in the current transitions, right? If my transition is triggered, whatever that transition is, right? Then and then I want to say that the triggered, which is this thing, is equal to the transition. So triggered is of type transition, which starts off as null pointer, right? But triggered right, is basically going to assign itself to the transition that we're going to. All right. Triggered is just a transition that has nothing right now. Initial trigger, the initial transition that's triggered. There's nothing, right? That's what it is. All right, and then if triggered, so if this exists, if it's not null, then our target state is equal to the triggered get target state. Whatever that triggered, whatever that transition is, that's going to equal to our target state. We're not quite there at that new state yet. We're just saying we're pointing to that new state. We're saying that the target state is equal to that new state, whatever that new state is. That's being passed in from the triggered action. Okay. And then what we want to say is that actions, going back up to here, actions is equal to the current state, whatever the current state is, right? So let's say, for example, idle. Is there a set of exit actions? What do I do if I'm exiting from idle and I'm going to attack? Do I do something? And it could mean things like I change my animation, I move from a idle animation to a attack animation or a run animation. If I'm going from an idle to attack directly, or if I'm going from idle to move to attack, if that's the state, move to player. Let's say that's the attack, or that's the action. Then maybe I change it from my animation from an idle animation to a move animation type. So that might be triggered on exit, right? Okay, cool. What else? And then actions. I add all the new state, the new transition actions, right, from the new state to the current state. So I kind of add them into the actions array, right, as an example. So I add them into the actions array, and then I also add in any entry actions for the target state. So I have my old actions, I have my all my actions, whatever actions are there in the triggered state and the transition part. And then I have all of my entry actions. So entry actions might be, okay, when I start attacking, I have to stop moving. I have to, there might be some additional actions I have to do, and you can put them in a very complex or a very simple way into the entry actions if there are any. Okay. If there's no entry actions, then it would be nothing. You would add nothing to this actions array. And that's what's happening here. And what I'm doing here is I say now the current state is equal to the target state. So my current state is equal to target state, which is the one that I'm looking at. So I'm going from idle, let's say, to move to player, right? And we'll kind of map this out in a second. And then I'll return that list of actions, whatever the list of actions are. So that's what happens. So I have this list of actions that I'm returning. And notice that the update function returns an action array. Okay, let's keep going. And then, then it says, so I'm returning actions if something's triggered. Else, I'm not returning anything. I'm just returning the current state actions that I'm doing. So whatever the actions are from the current state, there's two return statements here, one here and one here. And these, one or the other, is going to be returned out by the update function, depending on if I have one or more actions that I'm doing. Now, sometimes there's only one action. So your array is not really an array. It's like, okay, I'm patrolling, right? But a lot of times there's also other actions. Remember, let's think about all the possible actions you could have that you can break down, right? I have the physical locomotion. And let's break this out into a little graph again. So again, just think about the actions that could happen. So possible actions. So possible state actions, we'll say. So not, as an example, entry or exit actions, but let's think about these possible state actions. So one possible state action would be, let's say, for example, we're in idle state. Okay. What possible actions are there? Well, we have play the idle animation. So the idle animation is an action. That's something that has to happen. I play the idle animation. Maybe I even randomize, the idle animation. So, maybe I have a couple of different animations every little while, right? So have some kind of interval. Select a random interval, random interval. Maybe this is, as an example, what it could look like for idle, right? Play the idle animation for that interval, right? Whatever it is. And then maybe I'm going to, after the interval is done, select another idle animation, random idle animation. Maybe there's more than one. Like maybe the character, they're doing something idle. They're sitting down when they're in an idle animation. And there's another animation where the character is just looking around or looking bored, as an example, or whatever, right? Different kind of idle animations you can have. So I'm just giving you an example of some things that you can have. So these are possible idle state actions. Okay, what about entry to idle state actions? So this is the in-state actions. What about entry? There's going to be entry actions. So possible entry actions. And let's talk about what those are. So I'll put those up here, right? So let's do that. Put those up here. And let's talk about possible exit actions. Possible exit actions. Now, exit actions are going to be depending on, what I'm going to do. Is there something else I need to do when I'm, like entry is almost like setup and exit could be cleanup. Is there something that I want to set up in entry when I'm doing this? Well, I could say that a possible entry action would be to select a random idle animation. So I haven't really made the idle animation yet. I'm just selecting it. Just giving you an example of that. Could be an idle kind of an entry action. And then maybe exit actions. What I want to do is maybe shut down something, clean up, some kind of cleanup activity. So cleanup actions, where I want to clean up a animation, or I want to move something else, something else. So usually I have this kind of thing happening, right? And this is for one state. Now there could be, if I was to draw my state machine, let's suppose we're drawing that state machine from, instead of doing the what we've done before, as an example, where we were using decision trees, let's see if we can do that same group of states that we drew last week. Let's draw it instead with the state machine. Okay, so let's do that. And I'm doing this so that way it's clear for you guys how a state machine might work. Okay, and I say might because it really depends. So if we start in idle state. So this is our idle state, right? Okay, that's our idle state. And we're going to have an arrow when we draw the UML diagram that we want to draw from one state to the other. Remember that what we want to do is kind of mention the initial state, which is going to be the idle state, right? So this is the initial state. We want to draw a little circle as an example, and the little circle is going to be filled usually with a kind of black fill. That's it. So this is kind of what it looks like, idle state. Right, I'm putting it over there so we can think about the next state as I'm moving these around, just to give us some more real estate. Okay. So yeah, so what's the next state? Well, the next state is what's going to trigger me out of being idle, as an example, into something else. Now, remember, there is no idle state in our assignment 3. It's patrol state instead of idle state. So let's be more realistic. So we're into patrol state. There is no idle for this RAIs. RAIs are always patrolling. Okay, they don't stand around. So let's see if that actually fits there. It may not, but we're going to make it fit because we're going to do one of these patrol state. There we go. So we're in patrol state. That's where we are right now. And then what's going to trigger us to go into a different state? So what kind of triggers can we have? Right? Well, we can have 2 triggers, right? Line of sight or some kind of detection radius. Those are 2 triggers. That means there's different kinds of transitions that can occur, right? So again, I don't ask myself, do I have line of sight? It's, do I have either one or the other? There's going to be a trigger potentially for one or the other or both, right? So that's how it works out to be. So remember, there's 4 cases. I have line of sight. I don't have line of sight. I have I have, I mean, the player's in radius, the player's not in radius. I have line of sight, but the player's not in radius. I have the player's in radius, but I don't have line of sight. Okay. So let's draw a couple of transitions here. So there's one. Maybe we draw it with some right lines. How about that? Or with some dark colors. How about that one? So we'll draw it here like this. There's a transition, and we'll make it so that it is an arrow, as you know, carefully as I can make arrows right now, right? So with this little limitation. All right, so the first thing is going to be inside the line of sight. I have line of sight. That's the trigger. So let's put that in is, so has line of sight. That's the trigger. If I have line of sight, it's going to trigger me to transition between being in patrol state to doing something else. Okay. And what about the other thing? So what about the other state? Well, we can also have, I don't have line of sight, but I actually have, the player is inside of my detection radius. All right, so this is, I'm just drawing the arrows first, okay? And let's see how we can rewire this thing. So this is detection radius. I'm not putting question marks or anything else. I'm just showing you what it could look like from a you know, trigger perspective. And I'm trying to make it as tight as possible here, you know, so that way we can fit it all into this little thing. So detection radius is here, line of sight is here, right? And then what are the next states? Let's think about this together. Can someone tell me what the next state is from has line of sight based on the previous week's work? We talked about this last week. What do we do if the player has line of sight? So yeah, do I have to move to line of sight? Am I close enough? You know, those are the things that are a transition. So this is different now, right? Example would be if I've got detection radius, but I don't have line of sight. This might be easier to figure out. Then I need to move to line of sight. I know I've detected the player, but I'm out of patrol state. I need to move to line of sight. That's what I need to, because I want to be able to see the player. I don't know where the player is quite yet, but I heard him, or I somehow detected him. So I want to move to line of sight, right? That is the next action. So move to line of sight. Okay, so let's put that in there. And we'll draw this in a very simple way. So move to line of sight. All right, cool. What else? What about if I have line of sight? Well, I want to move to player, right? So that's the next action. Move to player, right? Thank you. People are seeding me with that information. I appreciate that. Move to player. All right, so move to line of sight, move to player. Those are two actions. Okay, so I'm moving to line of sight. And what about if I lose detection radius? Do I ever go back to patrol state? Not in our game. That's the answer. The answer is in our game, you don't. There's no way back to patrol state. Okay? Ever. We don't have that the ability for you to go back to patrol state. Why is that? Because what we're saying to you is that, you know what, we're creating a game where the enemy, once it detects you, is going to be continually moving towards you as much as possible, right? Because at the end of the day, what we want to do is, you know, we want to be able to get the enemy to attack the player, right? To make it more exciting. That's the idea behind it. All right, so move to player. Okay, when I'm moving to player, I'm in distance. I'm in the distance. If I've done the thing, do I still have line of sight? You know, can I move back to patrol state if I've moved to the player but they're gone? Well, no, I've seen the player, right? Kind of stuff. So now I want to transition. If the player is close enough, I want to transition to attack, right? So that's what I want to do. Somewhere I have to have an attack state. Let's put that in there because that's the next state, right? So the next state is the attack state. For this, I'm just going to hover right over here for a second, okay? So here's attack. And then we'll put that in there. So this is attack. And I'm not saying it's what type of attack, because our character in our last scenario did the same thing, right? Okay, so is there a way from us to get from move to line of sight to move to player? Well, now you can see has line of sight is a trigger that moves us to player. If I move to line of sight, do I have line of sight? I'm moving to a place where I think I have line of sight. Check to see that I have line of sight. If I do, then transition to move to player. So there's going to be a link between here, here, and here, right? Again, I'm just putting this out there, and let's see if we can optimize this little graph we're making as well. So here we go. I move to line of sight. Okay. So detection radius, I move to line of sight. If I have moved to from there, if I have line of sight, same condition, right? Then I move back to the player, right? I move to player. This is, again, think about the optimizations we might be able to make, right? Can I do it differently than this, right? And then from move to player to attack, right? So if I go to the other way around, let's just do that. If I'm close enough, then I'm going to go to attack, right? So this is kind of the way that we can get there, right? So attack. All right. So move to player, and then I go to attack, right? And the attack state, how do I attack? Am I close enough? If I'm close enough, then I attack. If I'm not close enough, I keep moving to player. I stay in the state, right? I keep moving to line of sight until I have line of sight. I'm keeping, remember, I only stay in one state at a time, right? So now I go into if I have, am I close enough? So close. I'm not putting question marks. I'm just putting just the name, right, to help us, right? If I'm close enough, that's the transition, then I attack, right? Cool. If I'm close enough, then I attack. If I'm not close, I stay and move to player. If I'm in patrol state and I don't have line of sight and I don't have detection radius, I stay in patrol state. Okay, I have line of sight. I move to the player. All right. I keep moving to the player. I keep moving to the player. What about if I lose line of sight? Right? If I lose line of sight, then I want to move back to move to line of sight. So that's one thing I need. That's also a possibility. I can go back this way, right? Because maybe I've already detected the player. And again, what we're doing is we're creating behavior, right? So let's make another arrow that goes this way. So there's another arrow, another exit possibility. So if I don't have line of sight, these are the conditions. I'm close enough, I attack, but I've lost line of sight. So lost line of sight somehow. If I don't have line of sight, then I want to move to line of sight. I want to move back to line of sight, right? So that's what can happen. If I have line of sight, I move to the player. If I like move closer, if I'm close enough, then I can attack. Otherwise, I can't. I can't get to attack from move to line of sight. I can only attack from move to player, right? There's no graph to get us there, okay? All right, what else? What can I do now? What's next? What about if I take enough damage and I take enough damage that I need to flee, right? Remember, I'm never going to go into patrol state, right? So maybe that's going to be an action, the flee action or whatever. But if you focus on this, these are the different actions that I can take. Move to line of sight, move to player, attack, right? Remember our last graph didn't look like this. It looked a little differently. And I have the one state, there's two states that have, one state here, move to player, that has two exits, two transitions, the attack transition or the lost line of sight transition, all right? Those are the two possibilities here, right? And the patrol state has two transitions. You can go to has line of sight or detection radius. I have detection radius or line of sight, right? Those are the two things I'm checking, the triggers, right? Move to line of sight, though, the only thing that I can do, right, is in this case, the way we've drawn this diagram is move to player. Here's something else. If I move to line of sight, But when I have line of sight, I'm close enough to the player. Can I attack? Would you allow your character to attack, or would you want him to put into move to player first, go into this state before attacking? It's really up to you. Because at the end of the day, if I say, oh, I just got line of sight, I'm going to move to player state. Oh, I'm close enough now. I trigger immediately an attack. That's okay too, right? Because it's going to happen very, very quickly. So that's something to note. So this is kind of our little state machine, and it talks about, now what about entry actions into move to player? Entry actions. Exit actions, I clean up from my patrol state, right? So I'm possibly, I clean up, I basically maybe choose an animation to move, maybe some random noises too. The first random step that I'm going to use to move from my patrol state to my move to player, I'm moving, right? There's a locomotion I'm having. Move to player and move to line of sight may have different animations involved in terms of selection, or they might have the same animation. That's okay, right? Move to line of sight has a whole pile of other things. What move to line of sight means is move to a node that has line of sight, right? Those are the current actions, right? The other thing that you want to also think about is, what about the exit actions? If I leave this one, sometimes the exit actions might be something like setting some booleans up. Well, I've left this one and I'm switching these things on or off, right? Because, for example, my boolean that might be something like, oh, I have line of sight. That's true now. So that sets to true. I had line of sight. Okay, cool. And by the way, there might be, when I move from patrol state to one of these two states, detected. Is the player detected? That might be a boolean that I have on or off. As soon as the player gets detected, there's no way back to the patrol state. That could be something that you want to kind of turn on an exit action, okay, as an example. So that's exit actions and entry actions and transitions, okay? But the very basic state machine might look like this. If you wanted to add other ones, for example, this might be a state machine for a close combat enemy, right, that we talked about in assignment 4, right? One other piece of the close combat enemy that they have that I'm not mentioning here is, what if I'm in attack state, right, as an example, and I'm getting hit, as an example, by I got too much damage, right? So I'm in attack state and I got damage. What do I do next? So is my damage, if I killed my player, then the game is over, right? I'm not going to continue playing. What if I got damaged? So if damage falls below a certain number, so let's say we'll put it down here. This is also something that can happen, right? So a new state, right, where damaged, we'll just call it damaged, where the damage means that this damage state means that you're in a spot that is, sorry, this is not the state, this is a transition. Let's try that again. Am I damaged too much? If I am, then I want to transition out of attack state, damaged. One more time. One more time. For completeness. Can I spell properly? I want to move from attack state, right? That's the trigger. If I'm too damaged, I move from attack state to flee state, right? Run away. And what are some exit actions that might happen out of attack state? Maybe when I move, I'm not running. If I see the player, maybe I run to the player. Where if I'm in detection radius, I don't run. I just move, like I'm walking carefully to find the player, I creep, kind of thing. Whereas here I'm running. Here I'm not running. Here I'm running. Here, if I've lost line of sight, I want to run. Maybe I'm running in these states here, but not in this state. And this state I'm definitely running, and this one I'm definitely running. When I'm close enough, I'm going to attack. Right? I move from running to attack action. Right? So I flee. And if I'm successful, then I leave the game. If I'm not successful, right, as an example, then I might die. But this might be the exit action that I go through. There is no way back to moving to line of sight when I'm damaged, in our case. Okay? And here's something else that might happen. If I'm in attack, what if I lose line of sight? What if the player runs away when I'm in attack action, right? So then I already detected them. I mean, I've already had them before. So guess what? There might be a transition back from attack to move to line of sight. Or if I have line of sight, but I'm not close enough anymore, then I want to move back to player, move to the player, right? So that's also something that might happen. So the attack action might have 3 little arrows that happen, right? Let's put those into play as well. Again, it really depends on how you want to program this, right? So let's say move to line of sight. How can I get there? How do I move to line of sight? Well, I lost line of sight. So lost line of sight. That's the same condition. Notice the condition is being used again, right? That's okay, right? Because that means, hey, if I lost line of sight, then I'm going to go back to move to line of sight, okay? All right, what about if the player moved away, but I still have line of sight? So player moved away, I need to, I'm not close anymore, then I got to go back, right? So I got to move to player. And if I lost line of sight, I go back to move to line of sight, okay? If I have line of sight, I move back to the player. See how this is working, right? So let's go to do this again. So we can see that there's a transition that moves us from this back to this, right? So, and how? We're not close. Not close. So that's kind of something that the player has moved away, basically. So either I'm close or not close. And if I'm not close, then I'm going to move back to the player. Not close means I've got line of sight, but I'm not close enough to attack, right? Lost line of sight means not only has he fled away, but I've lost line of sight. So which one is it, right? And sometimes what happens is this not close may trigger before lost line of sight is triggered. And sometimes what happens is in some games, maybe the player has the ability to go invisible, right? So is it not close or lost line of sight, or which one, right? So is it not close, lost line of sight, or damaged? And so you got to be careful about these and what they mean, right? The conditions are important to figure out. Okay, but is there a way back from move player to patrol? No, there isn't. Is there a way back from moving to line of sight back to patrol? No, there isn't, because we're not going to allow you to go back to patrol once the player's been detected. And so that is a state. We can say that when player is detected, then they are always detected. So once it's almost like the enemy knows the player's around. Until that point, the enemy doesn't know. It's not like you're going to have, this is a general rule, right? Where, some games allow you to flee, right? Maybe the patrol state might say, well, I don't know. I guess he's gone then, like in Skyrim or Oblivion, right? Wait, I heard something. Detection radius. That's what detection radius is. Let me go check. Look around. I don't see the player. So maybe move to line of sight. If you want it to be more intelligent, you can say, okay, what about if I never saw I've never seen the player. I never saw the player. I moved to try to find line of sight, right? I moved to investigate. That's what move to line of sight means. Close to where I heard the player, but when I got there, player was gone, right? So are they still in line of sight? Yes or no? If they're not, well, there might be another state that says player's lost. I've lost contact. Lost contact, go back to patrol state, right? If that's the case. So back in Skyrim or in Oblivion, I'm looking at that as an example, or Metal Gear Solid as an example. It's more like, I thought I heard something. Well, I guess it's gone then, right? So it's kind of like, to me, that is okay, but it can be really funny, right? You fire an arrow at a person's head, you hit them. Who is that? Then the guy runs at you to try and get you. And when they get there, you're hidden. You're invisible or hidden. And they're like, I guess he's gone then. Well, no, you're not going to ever go back. You're going to stay in alertness, which is what this is. Once the player is detected, you're going to stay alert forever. You're not going to just like go back to being quiet again, unless a long time has passed, So this is something where you can add additional states from move to line of sight. And same thing for move to player. Move to player, the player, you've lost contact, move to line of sight. From there, you lost the player, going back to patrol state, kind of thing. So there could be that kind of thing as well. So you can see the simplicity of state machines. State machines are really connected graphs, directed graphs, more than anything else, right? And it's like the ability for us to be able to, go from one state to the other. And that's why a lot of people use state machines for their initial AIs, because they're simple to understand. We know what kind of triggers that they might have from one state to the other state. I don't have to have a complicated structure for me to implement a state machine. All right. Let us continue. Okay. All right, so let's get back into this. Any questions around the stuff that we've talked about? I think this is important to, seeing this as maybe return patrol state, but its detection radius may rise. Yeah, maybe. That's a good idea too. I like that, Synod. Any questions around this basic structure for state machines? You should be able to draw out your game. Whenever you make a game, even the one for your game production that you're doing right now, as an example, you should be able to look at the game and say, okay, let's think about the AI. Let me map out that state, the AI states, worst case scenario. Remember, you can always take the states and actions and triggers and convert it into a tree. Always. Right? You can see that there's a lot of commonality here. We're having the same states, the same actions, really. It's really just about how you implement them. Let's get back. So state, the idea of state, there is a state class, and the state class has get actions, which return an action array, get entry actions, get exit actions, and get transitions, and they return different arrays. All right. Do we have something like enumerator? Yeah, we would have an enumerator as well, right? So each actions method should return a list of actions to carry out, whether it's an action, an entry action, or an exit action. Action is the current state action. There's entry and exit actions, whatever those have to be, right? And they might be other ones, maybe different animations or whatever it's going to be. And transitions from one state to the other. All right, transitions are just connections where you move from one state to the other state. Sometimes also in transitions, there's also transition actions. Okay. All right, so that is the way it works. So you can make this as simple as you want, by the way. You don't have to go so complex, but you can, right? So transition interface looks like this. Is triggered, all right? And then I have a get target state, whatever that is. It's going to return a state. What's the next track? That's the transition line. So that, when we go back to it, if I was to draw it, again, is these are the transitions. So detection radius, right? It's going to move from the transition from patrol state to move to player that is the new transition. And the new state is going to be move to player, right? So if I go back to that, see the target state is move to player for that kind of transition, right? Move to player transition is what this would be, right? And is triggered, that is true or false. Has the transition been triggered or not? Get actions, that are going to be the actions that are associated with the state that I'm moving towards. And get actions, remember it's a set of actions that are exit actions, entry actions, and the current actions. Right? So, and some kind of conditions. Conditions are also something that we can look at, right? So again, this is interesting. It says state machines are often defined in a data file and read into the game at runtime. And then one of the things that we want to try and make is we want to make a set of standard transitions where we have the data file that points to the next state, the next state, the next state. And the data file might also include things like enumerations that basically enumerate transition names. We can build up a state machine instead of hard coding a state machine. So I could, going back to this, hard code it so it works like this, just like we hard coded a decision tree, right? Or we can not hard code this. We can have a state machine, and what we can do is we can add state, add a transition, remove a transition, those kind of things from each state. as an example. So I can have two transitions, and each transition will have a condition that will trigger it. So if I add a transition, let's say I had an add transition method, that add transition method, when I build up my state machine, would also have a condition associated with it that would make it transition from patrol state to move to player. All right, and that's what it's talking about here. So don't hard code it. Hard coding is a bad thing, right? So unlike decision trees, state machines don't provide a simple way of combining tests to make more complex queries, right? It's only one test. Okay, it's not like you're combining a bunch of tests. If it's this and this and this, it's not like that. Here, what you're doing is you have a single condition, and the condition itself is going to be either met or not met. And so here's an example of the class transition, where you have actions, an actions array. You have a function that's getActions, which returns the actions array, right? You have a target state, again, which is of type state, and you're going to get the target state, which is going to return the target state, out from this action. And then the condition that is triggered, whatever the condition is, it's a condition type, right? And is it triggered or not? Here is the class condition. And again, you can make it from we're using object-oriented programming here. You can make a condition that is different types. So you can say that there's a floating point condition. So a number that meets the test with the test value that's going to be here. It's still going to return a Boolean. Is it passed or failed? If, for example, the min value, whatever that is less than or equal to the test value, is less than or equal to the max value, then it's going to return true, whatever that test value is. Okay, test value is something that you're going to use. You're going to set and get the test value. All right, so setters and getters for this type of condition. And there's other type of conditions. There's an and condition, a not condition, and an or condition. And you can kind of combine these conditions to create different kinds of tests, right? So this is pretty good. By the way, there's nothing wrong with creating these kind of conditions for decision trees as well, where you can combine different condition classes that are going to return a Boolean to determine if, I'm going to move from one state to the other. All right, so some weaknesses. Lots of method calls, right? Right now, we're looking at it being polymorphic. And polymorphic, once we start going using polymorphism and object-oriented programming, then it can slow things down and sometimes confuse the processor. For sure, it can happen, right? All this adds time, which makes it unsuitable for use in every frame on lots of characters. If I have a lot of characters with state machines, then there's a bit of a slowdown, all right? Now, again, slowdown won't be that great, but, slowly, some of this stuff can slow you down. So that's why sometimes we said trees are faster. They're the fastest way to make decisions, right? State machines are weaker, but they're easier to implement. And I mean, when I say weaker, I mean as in like they're slower. But for most of our games, state machines are just fine because we have a small number of artificial intelligent characters or agents, AI agents in the game, and all that kind of stuff. So it's just fine for what we're doing. But if you have a much larger game, you may want to consider a tree of some kind, decision tree or behavior tree, right? Where behavior trees are a little slower than decision trees, but have more flexibility. All right, and we also talked about this, a hard-coded state machine. That's how they all were done before, right? But it's become less common now because we want to make it so that it's more generic. I want to use the state machine class to create different state machines for different characters, right? I don't want to hard code my state machine every single time, right? So again, like I said, there might be things like I want to add a condition, remove a condition from a state. So a state might have that add a condition, remove condition, right? Add a transition, remove a transition, this kind of stuff from different states. And again, in hard-coded finite state machine, a state machine consists of an enumerated value and some kind of switch case a lot of times. So here's an example of a hard-coded state machine. You have an enumeration state with patrol, defend, and sleep, right? In this case. and you have your current state, whatever that state is. You have an update function, and all you're doing is checking. If my state is equal to patrol, then do something. If my state is equal to defend, then do something else. If my state is equal to sleep, then do something else, right? And then you can see what happens when I'm in patrol state. If I'm in patrol state, do I have line of sight? Can I see the player? Yes, then I want to go into defense mode. If not, then if I'm tired, then go back into sleep mode. So transition from patrol state to sleep mode. That's the new state. And when we go back down here, it'll transition to whichever state it is. Instead of using an if else again, I highly recommend using a switch case, which is a little bit faster. Okay, and function notify noise heard, right? That is something that goes into my hard-coded state machine, where if the noise is loud enough, if my state is equal to sleep and the volume is greater than 10, whatever the volume of the noise is, so if when I'm closer, maybe I make a louder noise, then I go right into defense mode, right? Whatever that defense state is, which is, whatever it's going to be that I do in defense mode, some actions. So that's a hard-coded state machine. So again, the update function happens each frame. Just going to move on to the next step. Okay, so weaknesses about hard-coded state machines. Easy to write, but they're really difficult to maintain. They can often get really large, right? And they can appear ugly and you don't know what they're doing, especially when they're coded in a switch case. All right, so that can happen as well. But remember, for me, if you were going to write a hard-coded state machine for your game and it worked, I might be okay with it. And the reason for this is it working? Because you remember, I always say to myself, get the game working. Always get the game working first, and then refactor afterward. Then you can decide, do I want to make a state machine class and then refactor my game so it's more flexible, more generic, so I can have more than one type. Now, in this case, for assignment 3 and 4, we're telling you there's going to be 2 different kinds of characters, autonomous characters. One type is going to be the type that is a close combat character, and the other one is going to be a ranged character. There's not going to be a character that has both close combat and ranged capability in assignment 4. We haven't given you that option. But if we did, then we can have different kinds of capabilities as well. We can create our own autonomous character. There's something also called hierarchical state machines, and these are where you have a state machine within a state machine. Okay, and sometimes what they can do is they can simplify the way our state machine works. So let's think about how this works. So here's search. I've seen there's a robot. In this case, there is a robot. The robot is a trash robot. Okay, so that's what this robot is about. Okay, and this is from the book. So the robot basically goes, okay, I'm doing some search. I'm searching for trash. Oh, I saw trash. Cool, I head for the trash. This is kind of similar to, I've seen the player, but I'm not close enough to pick it up. Okay, I'm near the trash now. Move to trash. Did I get the item? Yes, head for the compactor. And then is the item disposed? Go back and search for more trash. So a very simple state machine, right? That we have something that looks like this. But what happens when it is, in this case, they're adding some additional things. They said that, what if the robot runs low on power and has to scurry off to the nearest electrical point in the middle of a transition, in the middle of a state? That can happen. Something happens to disrupt the states that they're in. So if that's the case, we need some kind of alarm mechanism to move from one state to the other, and this can lead to doubling of the number of states. But instead of doing that, because remember, the alarm condition can be in every case, right? Which is kind of what we did earlier. So this could be what it looks like, but if I add a, no power to these things, look at how I'm duplicating. Remember I talked about this and when I drew my state machine, right? So no power, no power, no power, recharge, recharge, recharge. I have these alarm conditions that can go from get power, right? And then go back to whatever state we were in. So example, I'm in search mode and I have no power. So I have to go get power. but I'm getting power from search. Okay, cool. So I know the previous state that I was in. So get power, I want to go back after I'm recharged and go back to searching. Cool. So that's one state. And I'm doubling my states. Look, I'm doubling my states here. So instead of having 3, I have now 6. So the better way is to create a hierarchy of states, right? Where we have a bunch of states that move from one thing to the other. I'm just going to skip through here into here. So we have cleanup. This is the cleanup super state, if you will. I'm in, and this is inside the state machine. So I'm here in, remember my dot means, let's make this bigger for you guys. Remember what my dot means. My dot means this is my initial state, cleanup, okay? Cleanup is a hierarchical state machine now, where cleanup is I'm doing search, and I've seen the trash, I head for the trash, I got the trash, I head for the compactor, everything's good, and I go back and do it. Well, what happens if in cleanup state, which is the super state, as an example, notice that, by the way, when I go into this state, the default state for the cleanup state, which is the the child hierarchical state machine inside of this big one, right, is this. The default state is search. That's where it initializes. So we have a state machine here inside of another state machine. So I move, there's a trigger that triggers me to move out of cleanup state into moving to power. No power is an alarm condition that moves me out of cleaning up from any of these states. It moves me out of this, transitions me to getting power, right? So I immediately stop, I exit from one of these other states, no matter where I'm in search state, head for trash or head for compactor. I immediately exit from there. I use my exit condition, and I leave this whole cleanup state, and I go into getting power state. And then when I'm done, I go back into having power. I'm recharged. But now, instead of going back to the state that I was in again, I go back to searching. Because that's what this says. By default, I go back to searching. Now, the smart thing to do is when I leave from a state that's inside of cleanup, do I have a current state that I'm in? What current state am I in, right? Pass that information as an exit condition from moving from getting cleanup to when I'm getting power. So I keep track of what my previous state was. And then when I go from getting power back out, I'm going into cleanup mode, but I remember what my current state is. Notice there's an H star there. So there's some kind of heuristic that basically detects what previous state that I was in, and I move back into that previous state. If I was never in a previous state before, and this is the first time I'm doing cleanup, then I start with search. Okay. So again, they support transition between levels of hierarchy, and we need a bit more complex algorithms, right? Because otherwise we'll go back into something that doesn't make any sense, right? So here's also something called a cross-hierarchy transition, where you have a transition that takes you out of search, as an example, into getting power. So let's say I go around and I look around. My little robot who is looking around the base to clean up, as an example, they're looking around the base, and, well, they don't find trash after a certain time. They trigger the transition out of cleanup mode. Instead of just being, needing recharging or power, I have no power. I have some power, but I just go back and get some power and recharge back up to the normal, I top up basically is what I'm doing here, right? And then from topping up, there might be another state that's like me going into sleep mode, that kind of stuff. And then check every hour or every 2 hours for cleaning up perspective. All right, so again, what's the problem? We'd like an implementation of a state machine system that supports hierarchical state machines. We'd also like transitions that pass between different layers of the machine, right? Because the outer layer, this layer, right, has its own transition to go to get power or come back from power. But then there's the inner layer, which does its own little dance, right? So we need a transition between layers. So how do we do it? A lot of times we use recursive algorithms to do that. We don't have to. Again, whenever there's recursion, you always must think that there's a way to do it with a while loop. Chances are, if there's a recursive function, you can do it another way. but you could. Recursive functions make sense because it allows us to go from, from one state to the other and back. Again, first part of the system returns to the current state or returns the current state, and the result is a list of states from highest to lowest in the hierarchy. All right, and the state machine asks its current state to return to its hierarchy, and if the state is in a terminal state, it returns itself. So this is kind of like the recursive algorithm. And here's an example of different states that are inside of. So this is more generic. We don't care about the type of states that we have. We have some kind of state M, and this state M is outside of state L, and inside state L we have states A, B, C. But again, all we have ever is you're in one state at a time. Whether if you're in state L, that's the outside machine, right? The outer machine. The inner machine, you're inside. You can only have A, B, or C states. You start in A state, whatever A state is, because that's where it's telling you to go. Okay. The update is interesting because there's going to be two updates, right? There's going to be an update for the outer machine, which is state L and state M, and there's an update for the inner machine, which is state A, B, and C, right? So the inner machine basically checks every frame to see if there's a state change that we have to make because of a trigger, a condition that's triggering a different state, right? That's what happens every frame. Every frame we're triggering this, but at the same time, you're also running the outside update, and the outside update is also checking for power, right? So that's what's happening here. And these are all numbered transitions. They just created numbered transitions so that they're more generic. So you can see there's a transition here and here, but they're obviously going to make some more transitions between. And here's an example of a state machine. It's not the robot state machine, where you can only get to this transition, this state here, from outside, right? And there's no other way. Once you go here, there's also a way back out. But the only way back out is when you leave this whole super state, this top level. Notice that the arrow doesn't go from the inner state to the outer state. It goes from the parent state, as an example, to the outer state up here. So these state M, state N, and state L, M, and N, they're part of the outside or the top level hierarchy, where state A, B, and C are the inside or the internal state machine. Again, it can become confusing, but sometimes it can simplify our graphs as well. It talks about here how to code it. I'm not going to talk about hierarchical state machines in code too much because they're very similar in what we've seen. So I'm going to skip all these slides. This is for your viewing pleasure. If you're interested in the code, I think it's a pretty near read, maybe a few minutes. I'm just not going to go through it with you. All right, what about state machines with decision trees? How do I implement those? So we talked about decision trees before. As an example, can I add state machines in combination with decision trees? And the answer is yes, you can. So you might have, instead of hierarchical state machines, right? Maybe what I want to have is from my outside hierarchy, a decision tree. Okay. So what does this mean? It means that, okay, well, I might start off at a certain spot in the tree. Can the player see, can we see the player? Yes, that's such a decision tree. Then I go into, is the player nearby? Yes, then defend. Go into the defend state. And defend state might be a higher level state machine, right? That might have other underlying states inside the defend state, right? That we want to specify from a behavior perspective. Is the player nearby? No, then raise the alarm, right? Raising the alarm might call, other items, other enemies. So it'll trigger the alert state, right? Can't see the player, it triggers the alert state. And so then I go back to this state over here. Why? Because raising the alarm triggers this alert state. Alert state, can I see the player? So that means other AIs wake up. That's what happens when I raise the alarm. So a very interesting way of doing something with a combination of decision trees and state machines. And here is a state machine without decision tree transitions, right? So state machine by itself. So I do something like I have an alert. Can I see the player? And this is interesting. This is almost exactly what we've asked you to do. Is the player in sight, line of sight, but it's far away? If I'm far away, then raise the alarm. Because if I raise the alarm, then other people, other guards will be able to see you. Is my player in sight and are they close by? Then defend, or in our case, attack. Right? So those are two things that when I have line of sight, that could be almost like a little state machine itself, right? And that's it. Let's see if we can redraw our state machine and see if is there a way of simplifying this. Do you see some common things that we have, right? That we can, is there something we can, that we have the same as, right? Yeah, lost line of sight. We can lose line of sight. And what happens when we lose line of sight? We're searching again, which is this, right? Lost line of sight goes to move to line of sight. And really, if you think about what this is a search, right? So we're searching for line of sight. That's what this is, right? So, and I'm labeling this so that we can maybe it could be a superclass. How do we draw this differently? And here's an exercise, guys. We have some time, a few minutes. Take a few minutes now and take a snapshot here of my state machine, redraw it and post it, if you will, inside the chat. And what I'll do is I will take that and show it to the class and see what they think, right? If you have a second, I'll take a few minutes to do this myself too and think about this. So is there a way of refactoring is what we're asking. We don't want to do these transitions more than once because we have extra states. Now, the good thing is we've already broken it down into some kind of hierarchy. We've already done that. So we're never going to go back to patrol state, ever, right? Ever, ever, ever. We're never going to come back here. It starts here, but we never come back. So that's something of a thing as well. And if we think about that in terms of, kind of a super state, if you will, and let's look at that. So I have that kind of a bigger area here. If I was going to draw it, then could I not refactor where I say something like, well, okay, I'm patrolling. Do I have line of sight? Right, kind of stuff. I'm never going to go back to patrol, right? So really, I can make this a hierarchy where patrol will trigger, kind of like alertness. Here I'm in patrol mode. Here I'm in alert mode. I'm never going to go back to patrol mode again, right? When I'm alert, what am I doing? How did I get alert? Well, either I detected my character somehow. The player has been detected. I heard him or I saw him, right? So now how do I indicate this with the trigger, right? Well, it really depends on if I heard or saw, right? So if the player's been detected, this is the thing, right? So I can say, is the player detected? Oh, that means I either heard him or saw him, okay? And remember, I can do whatever I want in my case, right? There's no specific way of doing it. I'm looking at the patrol state as an outside state right now. I'm not saying this is the only way to do it, by the way, for refactor. But maybe this is what we can do. When we do our patrol state, if the player is detected, we don't know what's happened. We're never going to come back out here again. Once the player is detected, like this part right here, we're here for life. We're in there for the whole time. So we're never going to come back to this, which means now we have to detect if the player has line of sight or not. If the player has line of sight, it really depends on our state, right? So am I moving to the player or am I searching for line of sight? That are the two things that I'm going to have in here. So then let's put those in there. Those are the two states. And I think I like to start off whenever we're thinking about a state machine as, let's put all the states down, okay? So there is this state, which is going to be, move, right? Move to player, or we'll say close in, move to player. And this move to player state is what we have already, right? So move to player. I'm just going to make this smaller so we can fit it in here. So move to player. We know we have that state somehow because we have to move to line of sight. And the reason why this is going to happen is because you know, we don't know which one of these is going to be the initial state. The initial state depends on how I'm detected. Is it line of sight, or is it, you know, what's the condition? And then let's do the next one. So let's go on to the next P. We'll just draw it in the same way and then see if there's any savings we can make. So, or are we adding code here? This is another thing to consider, right? Are we making it more difficult, or are we simplifying in some way, right? So move to line of sight. Move to line of sight is here, okay? And the other one is the attack action and the flee action, right? So let's put the attack action here, right? And then there's the flee action. Guys, the flee action, the player will not be alert anymore. He'll be not in fighting ways. So this whole thing will be, you know, kind of alert, or, you know, willing to defend, or, you know, whatever it's ready, you know, ready to fight, right? So we'll call it the alert, being alert. Okay. So we know that if the player is damaged, they're not going to be in alert state anymore, right? They're going to be leaving. So there's going to be a transition out of the hierarchical state machine, you know, this thing right here, over here. This will be the flee action over here, right? Okay. And now we can see how this would work. I want to start with saying that if I have line of sight, then move to player, but I'm going to say that there's going to be a transition. So the initial state we're going to say is somehow the player's been detected. Chances are, I'm thinking that the player's been detected not by line of sight, but rather by radius, because radius has a higher chance of seeing the player first before line of sight. Again, this is my own personal choice. You may think to do this a different way. So I'm going to draw a little line here, right, as the first transition. This is my initial state. And this time, instead of drawing a solid circle, right, I'm really going to decide how I saw my player. So it's going to be an open circle with a little star inside of it, right? And that little star means it really depends. It depends how I start off. If I detected it with radius, then I'm going to move to line of sight. Yeah. Okay. That's what this part is. And we also know this. We also know that leaving, we can leave. We have an outside transition, a way of leaving the alert state by getting damaged. So we can say that there's definitely a way of getting the heck out of Dodge when we're damaged, right? Because when we're damaged, we're just going to get out of here, right? Because that means that's the thing that's going to trigger us, you know, to leave, to flee, right? Now you can see what's happening, right? It becomes a little bit, when we use hierarchical state machines, we haven't saved anything yet, but all we're doing is we are refactoring and we're simplifying in some ways on the outside. Now we've also added, this other box here is adding another layer of complexity, right? We can't be back to being alert, right? Maybe there's another thing over here that allows us to heal and then go back to patrol, right? But if we're alert, the whole machine says go back in there, get back into the fray, right? So there might be another way of doing that if we had something, some kind of healing mechanism, right? When I flee, you know, I leave the scene, you know, as an example, completely. Now in assignment 4, what we've said is once you flee the scene in a certain interval, you respawn and come back as something else. Another new one comes in, all right? That's another state altogether. But the new ones come in as alert, don't they? Not as patrol. And I think that's what happens once you raise the alarm, you know, kind of thing. Then you're out of patrol mode for only one of them. We don't have a state where they combine together. As an example, there's nothing like that in assignment 4 that says if one AI detects the player, all of them move to moving or searching now. right? So that's not something that we have, but again, it's something that you can always implement in your game. All right, so let's do this now. So let's think about the other states to simplify. So how do I move to line of sight, and then this one moves to attack. The only way that they can move to attack is by getting close, right? Now we're still going to have some similar states to move us back and forth. There's nothing that's going to change here, right? In terms of the way we've done it. We're not eliminating has line of sight or lost line of sight, right? That's nothing that's going to be eliminated. Either we're close or we're not close. If we're not close, then we're going to go back to moving to the player. So this is the other way around, not close. Close or not close, right? And if we're not close enough, that's going to be a trigger that's going to move us back to move to player. We still have line of sight at this point. So line of sight is still maintained. So we have line of sight. We have to, and if we're not close, then we're going to move to the player, right? We have line of sight, but we're close. We're going to attack, right? So in order for us to be in this state, we also have line of sight. Okay, so that's something of a condition that we're going to have to also think about. So that way, if we've lost line of sight, that is a condition that is something else we can put in here as well. Lost line of sight. Okay, well, if I lose line of sight, what happens? Right, well, then I'm going to move to another kind of state. So if I move to player, then I can go to attack. Okay, great. If I lost line of sight, then I go back to searching. This is still the same. There's nothing different here, guys, right? Last line of sight, we put that in there. So this part goes in here, the way we've done it here. But I'm asking you, is there another way you can do this? Is there something else, another way of losing and gaining line of sight? Is that an alert condition? Could you make that another hierarchy of some kind, right? Otherwise, you're just going to do the exact same. We're just going to draw the exact same state machine, just with less transitions, right? That's all that's going to happen, right? So let's go and say that I has line of sight and I lost line of sight. So has line of sight, let's just rotate it first and then move it back in there. Has line of sight and lost line of sight, right? So lost line of sight goes back to this thing. There's nothing wrong with these. I'm just saying that you can consider that there's other refactoring options for here as well, and we can draw the arrows. Again, I'm going into a lot of detail here because if we have a test that is a true-false multiple choice test, then I'm going to ask you these kind of questions, right? So move to line of sight, has line of sight, then I'm going to move to player, right? That goes this way. If I lost line of sight, I'm going to go here, which is move back to line of sight. And the only time I can attack is from move to player. So this is kind of our little state machine. It looks very similar to this one. All we've done is we've taken these pieces and put them in here. But one thing is we have an alert state and we have a state that is not alert. It's either fleeing or patrolling. So it gives us a different way of looking at the way of thinking about it. And a lot of times it's also a little bit simpler, right? Because a hierarchy allows us to to think about this. We're missing one more thing, missing a line that is telling us which part of this state machine are we starting, and we're going to start obviously in the patrol state. Whenever we have our new character come into play, then we're going to start in the patrol state because that's what we said we're going to do. And we can shade that as black. Okay. All right, so we've done that extensively. Any questions around this? All right, so those are the two options that I can see that are easy. This only flees if we get damaged. It doesn't mean, and by the way, here's something else. if we're damaged, we can be damaged in any state. Damage from move to player, damage from move to line of sight. Like, what if the player pings us from a distance? Right now, we're saying it's damage from attack, but actually, where this is better for fleeing is, and this is where hierarchical state machine works for us, is where we're saying that we can be damaged from anywhere, right? So we can be damaged from not just from the attack, but any state can create damage. And if we're damaged enough, then we can flee. We can stop any of these states we're in and move to fleeing, which makes more sense, doesn't it? Right? Because that is how it should be. It should be that, like, if I can get damaged, what if the player can see me, but I can't see them, right? So then when I'm moving to line of sight, when I'm searching for the player, they can ping me by getting damaged. I'm still trying to find the player, but I can't see them when they're hitting me with, let's say, snipering or something like that, right? Well, if I take enough damage, I'm not going to go to attack first before I leave. I want to be able to leave, right away. And this is where this state machine here on the top is not accurate, because flee, you should have damaged, flee, damaged, flee, damaged, flee, right? Even in patrol state. Okay, so this is where it doesn't make any sense, and this is where the hierarchical state machine makes more sense. Questions? All right, guys, so the first lab starts at 12. That's it for this week. Thank you so much for coming in. Again, take a look at this. I think there's some really great, very simple ways of understanding how this stuff works. And there's nothing wrong with using a state machine as opposed to using a decision tree or a behavior tree if you feel that makes more sense for your type of game. Okay. Now, some questions that were also asked. What do I mean by collider boundaries for debugging? And I'm a little confused. That was Sophia asked that question earlier. Let's see if I can answer that question here with a bit of explanation. So collider boundaries, that is in the debug area right here. So if you look at the debug, it says it'll show things like line of sight, rays, detection radius, and collider boundaries. The collider boundaries are for example, things like the shape of your collision detection collider. If you're using an AABB type collider, it'll be a rectangle. If you're using a circle type collider, it'll be a circle. That'll be your collider boundary. That'll look like it's green. It'll be like almost like it'll be a shape around your object. If you have a spaceship, and then if your collider boundary was an AABB type collider, then your collider boundary would be a rectangle that's around the spaceship. That's what I mean. So show me your collider boundaries. All right, and the other one was, Neil's asking, right now mine changes from idle to move on its own and travels on a random path. Should I change it to completely predetermined path then? No, I think it's okay to be a random path, but in the game it says there should be a predetermined path of nodes that it follows, right? And also it switches on when you press the P key when you're ready to patrol. So that's what it should be. How do we implement the node points on the screen? You don't implement node points on the screen. You implement node points in the game, and the node points are invisible. If you're going to draw the node points, if you want to draw node points, then you would just draw them as, let's say, little squares or little points, right? Little circles, if you're going to draw them. And the node, the thing that you're drawing is going to be overlaid on top of the actual position of the object. So let's say, for example, I have a node point at 1020. Then that would be the object might be much larger than that. Let's say, for example, my enemy, but I'm going to draw a little point there, a little dot or a little square or something, and it's going to be in that debug color, a green, like a really bright green color, as an example. Okay, anyone else have any questions around this before we move to our lab? All right, guys. Well, then I'll see you in lab. Lab starts at 12 o'clock, right? So 15 minutes from now, we'll get into that. Thank you so much for attending, and I'll see you guys on the lecture side next week. On the lab side, I'll record it during the second lab. Thank you.